Hey guys, it's Miss Johnson, and I'm here to bring you the first half of our notes for section 3.3. In this section of the book, we are going to talk about how to transform data that is not linear to start with, but we want to try to achieve linearity so that we can look at it on a scatter plot and look at the residuals and talk about the least squares regression model, because we can only use a least squares regression model when we have linear data. So if we start with data that's not linear, sometimes we can apply a transformation that will turn it linear, and then we can do some more analysis based on that. So in section 3.2, we learned how to analyze relationships between two quantitative variables, and that showed us a linear pattern. But when bivariate data, so when data that has two variables show a curved relationship, we must develop new techniques for finding an appropriate model. So in section 3.3, we're going to learn some simple transformations of data that can straighten a nonlinear pattern. Once the data have been transformed to achieve linearity, then we can use the LSRL to generate a useful model and make predictions. If you don't have it out already, today is a day that we're going to use your graphing calculator heavily. So I highly encourage you to grab that graphing calculator now so that we can work with some data. We're going to just go through one. We're going to talk about the different transformations, but we're going to go through one example and do these actual transformations. So it's going to be really useful for you to have your graphing calculator with you. So sometimes our data isn't linear. We want to transform the data to make it linear. We can apply a function such as a logarithm or a power to either one of the variables. We could do the x variable, the y variable, or both variables to achieve linearity. It's more than just changing units of measure. We talked, I think in section 3.1 maybe, that we could do transformations where you've got a multiplier and you add a constant. But this is more than that. This is taking a power or a logarithm, which actually changes the shape of the data. When we applied a multiplier or added or subtracted a constant, that didn't change the shape of our data. It would change how far it spread, but it didn't change the shape. This is going to actually change the shape of our data. And sometimes we can take our data from a curved relationship into a linear relationship, and then we can do a lot more analysis with that. So we're doing more than just changing units of measure, and we can take the log of x, the log of y, or both. So here's the first suggestion, or here's the first type of transformation, the power model. It says, when theory or experience suggests that a relationship between two variables follows a power model, you've got an equation that looks like y equals a times x to the p, whatever that power is. So transformations involving power models and roots can linearize a curved pattern in a scatter plot. So the option one could be raise the values of the explanatory variable to a certain power. And option two is take the p root, the pth root, if you will, of the values for the response variable. So those are just two ways that you can achieve linearity. Basically, you're taking your xy and making it x to the p times y, or then y, or you take your xy and make it x comma pth root of y. Okay, so that's one way. I would say that this is probably not the most common way. The most common way is to do a logarithm. So number two is a logarithmic model. So another useful strategy for straightening a curved pattern in a scatter plot is to take the logarithm of one or both of the variables. When a power model describes the relationship between two variables, a plot of log y versus log x, or ln y versus ln x, should be linear. Okay, so this is the one that we're going to be using. We're going to take the logarithm model quite a bit, or not quite a bit, but more often than the other two. The last one that is an option is an exponential model. So you could it says for an exponential model of the form y equals a times b to the x, the predictive values of the response variable are multiplied by a factor of b for each increase of 1 unit in the explanatory variable. When an exponential model describes the relationship between two variables, the plot of log y versus x, or ln y versus x, should be linear. So that's like if you're taking the logarithm of just one. So this really turns into a logarithm model in an essence anyways. but it's if you're just doing one variable basically. So those are the 3 different models. This is the one that we're going to use most often, and that's the one that we're actually going to do an example of today. All right, so I mentioned before to get out your graphing calculator if you don't have it. So here's our first example. We get a set of data. It says the data below shows the relationship between frying time and moisture content of tortilla chips. We want to graph a scatter plot. So the frying time is your explanatory variable, and then the moisture content is your response variable. So go ahead and plug those into your list. Now, you're going to use a whole lot of lists today in that stat editor. So I highly recommend that you put these guys in L1 and L2 because we're going to have to keep a lot of lists straight, and sometimes it's easiest just to start from the beginning. So go ahead and clear out your data. I have to clear out my data from last time we did an example together. So I'm putting in my frying time in L1. So 5, 10, 15, 20, 25, 30, 45, and 60 are my data points there. And I just like to spot check. 1, 2, 3, 4, 5, 6, 7, 8. Yep, I have 8 points and I'm on the 9th value, so I'm good. Now I'll go over and put my response variable into L2. 16.3, 9.7, 8.1, 4.2, 3.4, 2.9, 1.9, and 1.3. All right. So there's my LN1 and LN2. Now I'm going to go to that stat plot. I'm going to turn my stat plots on. Make sure you clear out the residual. If you did a residual graph the last time you did a stat plot, I'm going to change that back to L2. So I want my X list to be L1. I want my Y list to be L2 instead of residual. My residual was still in there from the last time. So then I'm going to go zoom 9 and get my scatter plot. If you have a line on your graph, I also have a line on my graph. It's probably the LSRL from the last one we did. Go into your Y equals and you can just clear out that line. You don't need it. So then I'm going to try zoom 9 again and see if it's better. All right. So here is my pattern. Here's my data. This is what it looks like. I'm going to hit the trace key because I like when my graph will tell me what the points are. So down here, I've got frying time in minutes, and up here I've got moisture content in percent. Okay, and I know I'm going from 5 all the way up to 60, so let's say that's 10, 20, 30, 40, 50, that's 60. 30, 20, 10. And then my highest moisture content is 16%. So up here, I'm just going to say that this is like 20. This is about 10. So that means that would be 5. That would be 15, and so on. Okay. So here's what my points look like. My points at 5, I'm up at 16. Right about there. At 10, I'm at 9.7, so almost the 10. At 15, I'm at 8.1, 20, 4.2, 25, 3.4, 30, 2.9, 45, I jump over to 45, I'm at 1.9, and then 60, 1.3. So take a look at that scatter plot. That's what the scatter plot looks like of your graph. We can very clearly see there that that is not a linear relationship. That is a relationship that is possibly exponential, possibly quadratic, but I would say it looks pretty exponential to me. You start up high, you come down low. It probably is going to level off. I don't think you can have a negative moisture content percentage. So I'm guessing it's going to approach 0 but never touch 0, which to me suggests that it's an exponential relationship. We don't really know what type of relationship it is. We can only make a guess. But we do know that it's not linear, and that's the important thing. Okay, so the next thing I would do is I'm going to find the LSRL for this relationship. Even though I know it's not linear, let's just take a look at what the LSRL would be. So go over, hit your stat button on your calculator, go over to calculate, and then do option 4, which is linreg. You want L1 and L2. And this is going to be important because we're going to need to do some logarithms from here too. So, all right, so here is my linear regression model. My LSRL looks like y equals I've got 11.9 for my y-intercept minus 0.22 times my x value. That's my LSRL. My R is negative 0.81. Now, when we think about correlation, negative 0.8 is not a horrible correlation. I would say that that's fairly strong. I wouldn't call it strong, but I would say it's fairly strong. So some people might look at this and think, oh yeah, you know, your correlation's pretty good. I could use that linear regression model. However, we can't just go off of R. This is just one of those examples of how you can look at R and you can use R as one of the tools that you use to assess whether this is a good model or not, but it can't only be based off of R, because when we look at the actual scatter plot, we can very clearly see that that is not a linear model. That's not linear data. So if I put in that LSRL right here, I'd have my y-intercept at 12 or 11.9, which is really close to 12, and then I go down 0.22. So that is down barely at all and over to 1. I mean, I'm going to end up with a line kind of like this. Okay, so it goes through a couple of the points, but it's not going to be a super awesome model for that data. We can very clearly see that that data is not linear and that we should probably work to get a better model. All right, so now that you've calculated the LSRL on your screen, we can go ahead and do the residual plots. So if you think back to finding the residual plot that we did in section 3.2, go up to your stat plot, go into stat plot 1, and go down to that Y2 list. So you're gonna leave your X list as L1, but in your Y list, you wanna find those residuals. Now the way you find residual is hitting the second vars button. No, I'm sorry, I lied. The second stat button. It's in the option called list. So second stat, which is list, all the way down at the bottom, which depends on your calculator. For me, it's option number 7. You may have other things in your calculator, but you're gonna go down to resid. So I put resid in that Y list, and then I'm gonna go to my home screen and hit zoom 9. And here's my residual model. And again, I like to hit the trace button because it's helpful to know what points I'm looking at. This is still the frying time in minutes. This is still my same X. But now this is the resid. So there's my residuals. So this is still going from 0 up to 60. So, you know, about halfway is 30, that's 10, that's 20, that's 40, that's 50, and so on. And then my residuals, looks like my highest residual is up at 5.5. So I'm going to say this is about 6. So that means this is about 3. And then if I go to my lowest residual, and again, I'm just hitting the trace key on my calculator to find that, I go down to about -3 there. I'm a little bit below the -3. So if I plot in my residuals, here's what they look like. At 5, my residual is 5.56. Now it makes sense to me that I have a really far residual because in my exponential model that I was looking at, or what I assume to be an exponential model, that very first point was really far away from my LSRL. That very first point was high up above the LSRL that I put on the graph. So it makes sense to me that that residual is pretty high. Then the next residual is pretty good. That one is barely above 0. That was the one for 10. Then at 15, I'm at -0.3, and even that one's pretty good. That's really close to 0. But then we start to get further away again. So then I'm down at -3 something for the 20, and then 25 is -2.8, which is really close to the 3. 30 is -2.23. The 45 looks pretty good. So 45 is just above, but then 60 gets far away again. So 2.89. Okay. Now here's the thing about residuals. You want to see random scatter. When I look at this residual, I see that we have a curved pattern that appears to be slightly quadratic. I could probably come up with some sort of quadratic model to go through a lot of those points pretty closely that very clearly has a pattern to me. I start up high, I go down low, and I go up high again. That's a problem. That tells me that my linear model is bad. Okay, so that's an important thing. That's what tells you you need to come up with a different model. All right, so here we go. Now we're going to start to transform our data. So we're going to go back into our stat editor and we're going to re-express our data using the log of y. Start with the log of the response variable first. Sometimes that's enough. If you do the log of y, sometimes you can transform your data enough that you don't have to do the log of x. Okay, so I'm going into stat. I'm going into edit. Arrow over to L3. So under L3, okay, you want to arrow up so that your cursor is blinking on here. So you'll see that like your cursor, or not blink, it doesn't blink, but it's highlighted. This whole L3 is highlighted, okay? I'm gonna hit enter. And when I do that, my L3 down at the bottom of my calculator, there's where my cursor is blinking, okay? So you should see your cursor blinking down at the bottom of your calculator. Here's where you want to type in the log, hit your log button, and it's going to open up, and then you're going to hit L2, which is, L2 is second and then above the 2, okay? And then hit enter, and it's going to auto-populate the logarithm of every value in your L2 list. So you should see all 8 of those values pop up. So great, good. Now I can go ahead and change my stat plot. So go into stat plot, go into plot number 1. I'm gonna go down to my X list and Y list. I have residuals in my Y list right now, but I wanna clear those out, get rid of that residual. And I'm gonna put in L3 instead, because now I don't want L2 anymore, I want L3. So this is gonna be frying time in minutes still. I haven't changed the X. But over here on the Y, this is going to be the log of moisture content. And that's still a percentage, okay? But now I'm doing the logarithm of it, not the, and you have to identify that as such. You have to write that out in your labels. Okay, one other thing I forgot to do, let's go back and do this. Let's do an LSRL of this new data. So hit stat on your calculator, go over to calculate, go to linreg, which is option 4. Instead of L1 and L2, I'm gonna do L1 and L3. And L3 is above the 3, so do second 3, and then I calculate. So here's my LSRL. If I write out that LSRL, be very careful that you identify what you've transformed. So I'm not looking at y anymore, I'm looking at the log of y. So the log of y is equal to, my y-intercept is 1.14, we'll call it, and then minus 0.02 of x. And I haven't transformed the x, so the x stays the same. But again, just like you have to identify the log of y in your graph labels, you have to identify the log of y in your LSRL. Okay, but check this out. Check out your correlation. Your R value jumped, it was negative 0.81, now it's negative 0.95. That was a big increase. That's really great. We want it to get closer to 1. The closer we are to 1 or negative 1, the better our regression model is. Okay, so now let's go look at our stat plot. So I'm gonna go to stat plot, I'm gonna go on, I'm gonna do, my stat plot 1 is L1 and L3, then I hit zoom 9, and here are my points. Again, you can trace. I like the trace button. The trace button tells you exactly what those coordinates are. So I'm still going, 0 up to 60. This is my 0, here's my 60. That means this is 30, 20, 10, 40, 50. But now my y values only go up to 1.2. So that would mean this is 0.6 and so on. Okay, so here's my graph. My first value is 5 and 1.21. My next point is 10 and 0.98. Right about there. My next one is 15 and 0.90. Then I have 20 and 0.62. Then I have 25 and 0.53. 30 and 0.46. 45, it jumps over to 45. 45 and 0.28 roughly. And then 60 and 0.11. Okay, so there's my model. Now, if I'm looking at this model, and I'm going to be really honest and ask myself, is this a linear model? It definitely looks much more linear than the first one. I will say that. However, it still looks like there's a slight curve. If I had to be honest with myself, it still looks like this has a little bit of a curve wrapped off towards the end. So it's definitely better, but can I say it's a perfect linear model? No, I don't think so. So could we do better? Yeah, I think we can. So then, well, and let's do this. Before we really decide that, let's do the residuals. So I'm going to graph the residual plot. So you've done the LSRL for L1 and L3. Now you need to go into that stat plot and you need to do L1 and the resid. And remember, you get residuals from second list, and that's option 7. And if you, this only works, by the way, the residual plot only works if you've most recently done the LSRL that you want to graph the residuals against. If you didn't do that LSRL that I just did, then you're not going to get the right residual plot. Okay. Oh, see? And now I just graphed my residual plot, and here's what it looks like. So I'm still looking at frying time in minutes. And now I'm looking at the resid of log of y. So not the resid of y, but the resid of log of y. So here's 0, here's 60, here's 30, there's 10, there's 20, there's 40, there's 50. And my residuals, I'm gonna hit the trace key. My residuals are a lot lower, which is great. We really want them to be down a lot closer to 0. So I only go up to about we'll call that 0.2. So that's 0.1. And then my negative ones go down to negative 0.13 or 14. So I'll say this is negative 0.2. There's my negative 0.1. Okay, so if I graph my points look like this. This is 5 and 1.6. Then I have 10 and 0.03. Pretty close. Then I have 15 and 0.05. Then I have 20 and negative 0.13. 25, negative 0.13 again. Put a little bit higher. Negative 0.10. 30 is negative 0.10. 30, nope, then 45 is really close to 0, which is awesome. And 60 is 0.12. Okay, so again, when I look at this, it does not look like random scatter to me. That's the goal. We want it to be random scatter, and it's not. So I'm seeing that there is a little bit of a curved pattern through this. It again looks like it's quadratic of some kind. So I would say that I can still do better. I can still do better with this model. All right, so we have one more thing to try. All right, so now we're gonna go back, and instead of just leaving our x's alone, now we're gonna actually mess with our x's and change them into log of x. So log of x is gonna go into your L4, and here's where you really need to pay attention, because now L4 is gonna be the new x variable that you want, and L3 is going to be the new y variable. So go into your stat editor, stat edit, here, arrow over to L4. So I'm stat edit. Go over to L4 and arrow up so that you're highlighted on the actual L4. Hit enter so that that L4 down at the bottom has your blinking cursor. So you should see your blinking cursor down at the bottom. Now you're going to type log of L1, because that's going to give you the log of your x values. So log of L1, and there they are. Okay, then you hit enter. So there's your calculator keystrokes. So now let's go just look at the stat plot. I want to go to second stat plot. I want to turn that on, get rid of your residuals, and get rid of L1. You don't want L1 anymore. You want L4. So you are doing a graph of the log of x, which we just put in L4, and the log of y, which is L3. So your x list is L4, and your y list is L3, because that's what we did in the last part. All right, so let's go second quit. I go zoom trace or zoom stat, which is option 9, and check that out. You got a really nice, pretty graph. Oh, I always forget to do this too. Go over to second calculate and do option 4, linear regression, and change your linear regression. So do lin reg. I'll come up here. Lin reg. This is from stat. Arrow over to calc. Lin reg is option 4. And you want your x to be L4. And then your y is L3. So I'm going to change my x list to L4. My y list is L3. And I hit calculate. Look at your R. That's really good too. So here's my LSRL. I've got the log of y is equal to, my y-intercept is 2.01 roughly, minus 1.05 times the log of x. Don't forget to put in log of y and log of x for your LSRL, because it's not just x and y anymore. It's the log of x and the log of y. So there's my LSRL. What's my R? R is negative 0.988 roughly. So that's great. Yay. That's a really nice correlation. And check out your graph. So now I'm doing the log of frying time and the log of moisture content. All right, so this is now, oh, it's not 0 to 60 because I changed my x's. Let's go back to my graph. If I trace this, I go 0 all the way up to 1.8. So I'm going to say 0 to 2. Here's a 1. My y's, if I'm using the trace, I see my y goes up to 1.2 and then down to 0.11. So I'm going to say that this is, I need to be in blue here. This is my 1.2, we'll say, and that I think I put a 0.6 on the other graph. Yep, so we'll do 1.2, so then halfway down would be 0.6. All right, now let's graph our points. So the first one, 0.6 for my x, 0.7 almost, and 1.2. So I'm like up there. Then I go to 1 and 0.98, 1 and 1 basically. There. Then I go to 1.17 and go to 0.90. Then I jump a little bit. I go to 1.3 and down to 0.6. 1.3 again, or 1.4, I guess I could say. 1.4 and 0.53 is a little bit lower. 1.5 almost, 1.47 is what I'm looking at. And the 0.46, and then 1.6. My scaling is a little bit off, and I apologize. 1.65, and I'm down to the 0.2, and then the last one was 1.78. So my x values got a little spaced out more than they needed to be, but you get it. The point here is it's definitely a lot more linear. Definitely a lot more linear. Our correlation is much better. Our LSRL, we could even put that LSRL on the graph. If you go back to your home screen and you let's put that LSRL in my Y1 menu so that it graphs your line on top of your scatter plot. So hit the stat button Here, I'll try to give you some keystrokes here, because I know this is really hard to do without seeing what's happening. So stat, and then calculate. And then you're gonna go to option 4, which is the linreg. That's where we already did this once, but we're just gonna do it again to put that line in the right spot. So you should have L4 and then L3, where you see store regression equation. Store regression equation. That's where we want to get that Y1 in there. So this is where you hit vars. So put your cursor next to store regression equation. So your cursor is right here blinking. Hit the vars button. Sorry, that was a bad B. Vars. And then over to Y vars. And then enter on function. And then that's where you see Y1. And that'll pull that Y1 into that stored regression equation position. Then you can hit graph again. You've already done zoom 9, so it should already be there. But if you hit graph, you're gonna see your LSRL go through, just like my green line there, and it looks really close to those points, and it looks really nice. That's a really great linear model. We could even go one step further and do the residuals. So let's take a look at the residuals of that plot. Go into your stat plot, leave your L4, now go to the Y list and do residuals. So that was in that second list. Stat plot, my Y list, I go second list, and I want option 7, which is resid. And then I go zoom, and I do 9, and it looks a lot more random. It still doesn't look totally, absolutely perfect, but it definitely looks a lot more random. I'm not gonna do the whole scaling and all that, but just know, like, here's what my residual plot looks like. My residual plot looks kind of like that, and then there's a bunch down here and a couple that are really close, and then one down here. So it's definitely much more random. It definitely bounces around a little bit more, and we're only looking at 8 points, so it's a little bit hard to tell what it should be, but it still looks more random. And this would be the log of frying time and the resid of the log of moisture content of the chips. That's what my Y value is. So when we get to this last little piece of what we've done all this work to transform these models. We've done all this work to transform the data. We've got it to achieve linearity. We've gotten a nice correlation that's really close to 1. Our residual plot looks pretty good. The whole point of all of that is to get a prediction model. That is the reason. So using the best model, predict the moisture content when fry time is 32 minutes. So I would say the best model is by far that last one that we did. I'm gonna go back and pull that LSRL again. It was LSRL of L4 and L3, and it looked like this. And we can even use that linear regression where we put it into the Y1 and you can find your actual value. But my LSRO would look like this. It's the log of Y equaling that 2.01 minus 1.05 times the log of X. Okay, so if our fry time is 32 minutes, I'm going to take 32 minutes and I'm going to plug it in for X right there. So I have the log of Y is equal to 2.01 minus 1.05 times the log of 32. Let's go ahead and calculate that right-hand side. Log of Y, so 2.01, I didn't get my decimal the first time, minus 1.05 times the log of 32. So I get the log of Y is equal to 0.4296. Keeps going, but we'll just call it that for now. Now, if you think back to logarithms, you've got the log base 10 of Y is equal to this. If we want to undo this log, that means we need to take 10 and raise it to that power to equal the Y. So I'd have 10 raised to the point 0.4296 is equal to y. And I'm just going to leave the decimal that's on my calculator and do 10 raised to that power. And I get y equals 2.69%. If you think about it logically, that makes a lot of sense when we're saying that the fry time is 32 minutes. 32 minutes seems like kind of a long fry time, which means that your moisture content is probably going to go down. So if I were to graph that point, 32 minutes, into the graph, and I put 2.69% as its y value, it probably falls in line with that curved pattern that we had on our first original scatter plot of the x and the y. The other thing about this is we are not extrapolating because 32 is in our x range of 0 to 60. Well, really 5 to 60. So our x values went from 5 to 60 and 32 minutes falls within there. So I know I'm not extrapolating, which is good. I didn't pick a value that's way far outside of our pattern, and I can give a fairly accurate prediction that I'm confident in, because I know that I achieved linearity and I know that my model is a good model, my residual plot looked good, and my correlation was pretty high. So, woo, that was a lot of work. So if you made it all the way to the end, congratulations, give yourself a pat on the back, because this is a really hefty section with a lot of calculator work. Thanks for listening, and we'll finish up this section in our next video. Catch you next time.